As mentioned before, self-supervised learning is a branch of unsupervised learning where data provides the supervision. It tasks the network by predicting the withholding part of the inputs. For example, one can predict the future from the past, predict the masked from the visible, or predict any occluded part from the available part. Self-supervised learning on large-scale unlabeled audio enables the model to learn meaningful representations, which can benefit a wide variety of speech processing tasks, such as automatic speech recognition, speaker verification and intent classification. Several self-supervised pre-trained speech models have been proposed. Contrastive predictive coding, or CPC, predicts the future representation from the past in a contrastive learning manner. Wave-to-Vec2 masks the speech input in the latent space and solves a contrastive task to predict the representation of the masked part, where the latter is similar to CPC. Terra, on the other hand, applies masking to the input acoustic features in both time and frequency domain, and the masked part is then regenerated from the output representations. In this work, we explore the potential of several self-supervised pre-trained models, including Wave-to-Vec2, Terra, APC and CPC, for speech quality assessment. And two datasets are involved in the experiments: Voice Conversion Challenges 2018 and Voice Conversion Challenges 2016. In both datasets, opinion scores are given to the synthesized audios from different participating systems based on the audio quality. The score of each individual judge for each utterance is available in VCC 2018, while VCC 2016 only provides the system-level score. Intuitively, if the representations from a self-supervised pre-trained model are more discriminative between the high and low-quality audios than conventional features are, they are more likely beneficial to MOS prediction. We sample synthetic data from the best and the worst systems as well as ground truth in VCC 2018. Additionally, we also collected real-world noises and music from other datasets. Then we extract their representations with Wave-to-Vec2 and project them to 2D space using TSNE. From the results, we can see that the real clean speech clusters together with audios from the best system while being far away from that of the worst system, noise and music. This suggests that Wave-to-Vec2 can classify different kinds of audio, and synthetic speech sounding more realistic tends to be closer to the cluster of real speech. We further extend the analysis on four aforementioned pre-trained models using canonical correlation analysis, or CCA, which finds a linear transformation that maps the representations to scores, while maximizing the linear correlation between these estimated scores and the ground truth. For each utterance, the utterance-level representation is generated by averaging all of its frame-level representations. We then perform CCA using these utterance-level representations on VCC 2018 training set and apply the found transform on VCC 2018 testing set and VCC 2016 for generalizability. We also included two conventional acoustic features, MFCC and MEL spectrogram, as the baseline. For VCC 2018, we can see that the utterance-level correlation on these representations is much higher than the baseline, which implies they contain information about audio quality. Moreover, the correlation also remains high on VCC 2016, suggesting that these representations are general to evaluate audio quality. With both qualitative and quantitative analysis, we can know that it is useful and feasible to use self-supervised pre-trained models for MOS prediction. When predicting the MOS score of an utterance, we believe that it is more reasonable to score segments of utterance instead of every frame, as the former one correlates better to human perception. Hence, as previously described, a self-attention pooling layer is adopted in the downstream module to obtain the segment-level representations from the frame-level representations. In self-attention pooling, the keys and the values refer to the same representation. Given the frame-level representations, we first obtain the queries by taking dot product with a trainable weight matrix, followed by softmax. And the segment-level representation can be determined by taking dot product between the queries and the frame-level representations. Therefore, the segment-level representations is actually the weighted average of the frame-level representations, where the weights correspond to the alignment learned by the self-attention mechanism. Besides, utilizing the individual judges' scores in training has been shown to improve the performance, as it can capture the personal preference and thus stabilize the training. Here we also adopt a bias network to make use of them. In the bias network, the embedding corresponding to the individual judge is first generated by a trainable embedding table. Then it is added to the frame-level representations to form judge-biased representations. Finally, we can determine the bias score of a judge from the judge-biased representations with the downstream module. And the judge score is simply the summation of mean score and bias score. We first evaluate the proposed framework with 4 pre-trained models as well as the baseline, MBNet, on VCC 2018 test set. In terms of MSE, all of our models outperform the baseline significantly in both utterance and system level, which shows that our models can predict more accurate scores compared to the baseline. In terms of linear correlation, our models correlate better in utterance level, while yielding better or competitive results in system level. As for rank order correlation, our models as well surpass the baseline in utterance level, while falling slightly behind yet being competitive to the baseline in system level. The results in LCC and SRCC suggests that our models are able to distinguish utterance with different qualities. We then evaluate the generalizability with system-level LCC and SRCC on VCC 2016 dataset. We believe that LCC and SRCC better evaluate the performance than MSE does, since the latter cannot capture the positive and negative correlation between two sets of samples but only reflects the absolute difference. In terms of LCC, our models are at least comparable to the baseline, and Wave-to-Vec2 and CPC even surpass much. As for SRCC, all of our models have better performance compared to the baseline, except CPC. Overall, our models work better than the baseline on VCC 2018 and show well generalizability on VCC 2016. Moreover, Wave-to-Vec2 seems to be the best among all the models. We further inspect how each module works by removing them one at a time. When the bias network is removed, only the mean score of each utterance is used in training. The performance of most models are slightly worse in both LCC and SRCC, suggesting that using individual judge scores is an important key to better MOS prediction. In the case audio segments are not used, we directly calculate the utterance score from frame-level representations. We can see that the performance dropped for almost all models, especially for Terra, showing that segment is a better unit for quality assessment than the frame is, as we mentioned before. Then, when we replaced the attention pooling with a simple mean pooling layer, there is little change. This is probably because we adopted segment-level MSE in the training objective, which enforces all segments in an utterance to give similar or same scores and therefore weaken the power of attention. Last, without the presence of range clipping, the range of mean score is no longer limited and therefore can be any real number. We can observe that the results worsen for almost all models. This means the clipping works well for stabilizing model output within a reasonable range. To sum up, since the collection of MOS requires intensive crowd work and is time-consuming, there are demands for automatic quality assessment. In this work, we present the first use of self-supervised learning for MOS prediction. Our framework outperformed the previous works on VCC 2018 and show well generalizability on VCC 2016. We also conducted a thorough ablation study showing that each of the modules is working well. Thanks for listening.